So you've acquired this nice vintage machine, possibly from the late 70s or early 80s, and you're interested in learning how to program it as compared to just using prepackaged or homebrew existing software. So the steps that you need to take in order to do that are very simple. First of all, you need documentation, documentation, documentation. And each machine has its own set of specific manuals, which also depend on the kind of programming you want to do, whether it's just basic programming or you want a more evolved higher level language like Pascal or Fortran, or a low level programming language, essentially like assembly language. So in my case, for this 4P, I basically downloaded a bunch of software manuals. Here we have the Zeus Editor Assembler for assembly language programming, the disk operating system manual, which is essential to learn how to actually manipulate disks on this machine, the basic reference manual, and the TRS-80 Pascal manual. This Pascal is usually my go-to programming language on these vintage machines. It's an evolved high-level language which is very flexible in the right hands and can produce a really neat code. In addition to these reference manuals, you also should have a few additional traditional books. I have here my Pascal textbook, which actually is the textbook I used in college back in 1983, I believe, to learn Pascal, and I still have it. And I also acquired a assembly language reference for the TRS-80 line, as well as a graphics book, which is primarily aimed for basic graphics development. You can obviously have a lot more, but for my purposes this was sufficient. And of course you need software to come with these manuals, and these can be downloaded from various sources, or you can even get them sometimes from specific individuals. In the case of the TRS-80, there's a great guy named Ira Goldclank who maintains a website, which link I'll put in the description of this video, and who does offer a free service for providing you with system software for the TRS-80 classic line of computers. If you do download software from the internet, you're going to need to have a way of transferring them to your specific machine. In my case here, I maintain a couple of vintage PCs. One is a 486 DX4100 machine with a 5¼ inch low density drive and a high density 3½ inch floppy drive, and a CD-ROM, of course, and a hard drive inside, actually 2 hard drives. And here's a Windows 98 machine. This one is not really used for transferring software to vintage machines. It's more of a games machine in general. You can use specific programs that can take a downloaded image for your particular machine and transfer it to a floppy disk, generally a 5¼ inch floppy disk. You know, the variety of tools for each different machine. If you have a CPM machine, for example, you can use the 22 disk utility, If you have a TRS-80 line, you can use the IMD suite for transfers back and forth, etc. You just have to do your research. So I'm going to go ahead and demonstrate how to create a Pascal program on the TRS-80 Model 4P here. So first you should start the computer. You should not have any floppies in the drives when you start the computer, because there's a chance they could get corrupted, and that's related to the magnetic field surge that's created when the computer first started on. Once your computer is on, you can insert your system floppies. Here I have a Pascal system disk, and I'll put also a work disk in disk 1. So you have disk 0 and disk 1, and then hit the reset button. That should get the computer booted, and we can get started from there. So the Pascal system I'm using here is the TRS-80 Pascal development package, which was designed specifically for the Model 4. And it has several different versions. It's got quite a beefy manual, and with a variety of functions. It's quite full-featured, and it's very closely hemming to the standard Pascal, but with additional functions specifically for the TRS-80 Model 4. Things like, for example, accessing the graphic screen, for example. Alright, so we've got the system booted up. First thing you want to invoke is the editor. So you can just type edit, and it'll open up a blank file at this point. And we're going to do the traditional hello world. For this editor, you have to actually create blank lines unless you go into insert mode. I prefer to use the overwrite mode. Let's go into caps lock. I'm a sucker for caps for these kind of programming. And we'll create our program. Hello. That's simple. We don't have any variables for this program, so we'll start with the begin clause, and we'll write line hello world. Okay, and we are, that's it. Very simple. Obviously this can get quite extensive, but for the purpose of demonstration this should be sufficient to give you an idea what it takes. So we've got our program, so now we need to save it, and there's a special command called ex, which we enter, and then it'll ask for a file name. Let's call it hello /PCL for Pascal, and we want it on drive 1, and we don't need to back up, and it'll just basically save it to drive 1, and then it'll exit the editor. Once this is exited, if you list hello /PCL, you should get the listing of the program, which is right there. So everything is good. Now we have a source code. Now we have to assemble it, and this Pascal package assembles to pseudocode, not immediately to machine language. You do have the option of converting it to machine language through a code generator. This is not really necessary except for really specific tasks. The pseudocode is definitely fast enough, and for most programs, using the code generator does not yield significant execution speed increases that are noticeable anyway. Alright, so to assemble, to compile the source code, just type Pascal and then the name of our program, and I usually put the drive where it's at, and it will just go ahead and invoke the compiler, and it will assemble. It shouldn't take any time at all, and no errors, thankfully. Alright, if there were any errors, it will indicate which line had the errors and what type of error that was, and you can go back into the editor and correct it again, and then repeat the compilation process. So now, if we do a directory of disk 1, you notice that we have our hello./pcl source code, and now we have a hello.object file source code, which is a pseudocode generated by Pascal. And this can actually be run using the Pascal runp command. I should say for this package's runp command. So we can do a runp hello, and it should it'll accept, it'll default to the /obj extension, and it should print hello world. And it'll ask for input and output redirection. This is a quirk of this package. There's a way to get rid of that, but it is clunky at best, and I'm not going to demonstrate it here. You know, so I don't know why they did it that way, but it doesn't matter. It's not a big deal. And yep, there it goes from hello world, and then the program terminated, and then gives you some information about stack and heap use. All of these this information after the program ends, as well as the input and output prompts at the beginning, can be actually suppressed, as I stated before, but it's not a straightforward procedure, and but it's definitely doable. In any case, here's our hello world. Now, if you want to be able to distribute that executable without having the person running the program requiring the Pascal package, what you have to do is you have to link that pseudocode into a format that is actually executable directly. And for that, we have to switch over to the third system disk of the Pascal package, which contains the link load utility. That's basically a linker. So we're just going to load our hello/obj file, and it will load it. It's very simple. There are no other references. You can check the symbol list, and there's really nothing. It's just a defined program. So now we can build it, and it'll ask for stack size. Typically, I usually put 4 or 5K. For this is 4K. It's probably way overkill, but it's fine. We have the memory. And then it'll ask you for a target file, and so this time we're going to call it hello/cmd and on drive 1, and it'll just link it. Take a second or two. You notice even the fact that we are using only basically one-line program, it still takes a lot of time to process it between the editor, compiler, and the linker. There's a lot of disk access happening here, as you can see. It is what it is. So I would highly recommend upgrading the system to a hard drive or hard drive equivalent facility, which I will be eventually doing for this machine, because then it will save a lot of wear and tear on your floppy drives and make the compilation process and the development in general much faster. In any case, we go back and do a directory on drive 1, um, you'll see that now we have a hello. Oh, the CMD did not come up first. Oh, I put 2 slashes. That's what happened. Never mind. So let's correct that quickly. Let's remove hello. Yeah, the keyboard is a little flaky, and I fixed most of it, but sometimes it does do double strokes. So I have to be careful with that. So let's do quickly the link code again. Node hello /obj. Alright, and build 4K and hello /cmd drive 1. Okay, that should do it. I will let it do its thing here. So you're already getting kind of a feel of what it takes to develop on a vintage machine like that. Obviously the vast majority of people still will do this now on an emulator, where you can actually have accelerated drive access and even system speed multipliers up to maybe 10 times or more the original hardware speed. In my view, however, and that's only a personal view, I much prefer working on the real machine, because that's the whole purpose of this hobby, is to use these vintage machines and quote unquote suffer all their quirks. That's part of the charm. Again, you might have a differing opinion, and in the end you do what works best for you. This is what gives me pleasure. Alright, so let's go back to doing a directory of disk 1, and we should this time have the hello /cmd. So now all you have to do is just type hello, and we should get the execution of the program, and again the pesky input output things, and there we are, hello world. And that's essentially it. So yeah, it took us probably what, 10 minutes to develop and compile and link a one-line program, and obviously this can become prohibitively expensive in time and effort as your programs get larger. I did develop actually a program. I'll give you a quick demo of it while we're at it. It's called Boys, and that program is a flocking simulation based on an article published in the 90s, or the 80s, I'm sorry, about how to simulate birds' flocking behavior. So it just tries to simulate flocking of dots on the screen. It's interesting, but super slow, so it takes several hours to really start seeing the flocking behavior properly. But if we, for example, just list that program, you get an idea of the size and complexity of it. There's a lot of floating point math and trigonometry here, because we're dealing mostly with vector math, and there are no libraries available for TRS-80 Pascal for this. In any case, if we run it, you'll see that it does not ask for input-output redirection. I suppressed that, and it gives you defaults. In this simulation, basically, you can have what we call the local group for each void, which is a dot on the screen. It can only see a certain radius around it, and it can go from 1 to 50. I have the default of 20. It has a starting velocity of 5. These are unitless numbers. It can go from 1 to 30. separation between each void should not be less than 2, and this is where it'll try to get as close to 2 as possible from the other void surrounding it. And finally, the rotation, how quickly the birds or the voids can turn. You know, here I have it at the default of 90 degrees, which is relatively realistic. I think birds can do a quick 90-degree sudden turn. So once this is entered, then the simulation does the thing. We get a random distribution of voids, and then slowly, you know, they will start flocking based on the local radius, the velocity, the separation, and the rotation freedom. And eventually, over a couple of hours, you'll definitely see different birds flocking together. And it's interesting to watch. I mean, over time, this is best done obviously on much faster machines, where you can have a very fluid demonstration, and there are a lot of YouTube videos on this. But this was a fun exercise. It was the first program and the only program so far I've written for the TRS-80 Model 4. It was really highly educational and helpful in learning the intricacies of this machine. For example, I learned how to link assembly language routines to Pascal, because I needed to access one of the refresh register in the Z80 processor as a seed, to use as a seed for the random number generator, because TRS-80 Pascal does not come with a random number generator. Thing like that. I learned about the funny thing about the screen, the pixels and the graphic screen, where some rows display pixel as 2 as a rectangular vertical representation, and some rows it's only a single pixel. At first I thought there was something wrong with my display routine, but it turns out this was a quirk of the Model 4. This does not happen with the Model 3. It's just related to the way the character screen, because this is all essentially character based. It's the way essentially related to the characters, the way the character screen is laid out as far as height and width on the TRS-80 Model 4. Alright, I'm not going to get you through to suffer for a couple of hours watching this, but essentially this is what it would take to program this machine. No, it's not easy, I wouldn't say that, but if you're interested and determined, you certainly can do it, and it'll give you a very good idea of what it was like back in the late 70s or early 80s to actually come up with workable programs on these wonderful machines. Alright, that's about it for now. Thank you for watching.